Welcome back to the Deep Dive. Today we are really opening up the black box of LLM infrastructure. We're diving deep into retrieval augmented generation, RAG. This is the tech that makes large language models actually useful in the real world. It pulls in external, up-to-date info.
Yeah, so they're not just like stuck with old training data or hallucinating.
Exactly. It's crucial for accuracy, for relevance.
It absolutely is. But RAG has this fundamental problem sort of baked right in.
Okay.
The whole idea relies on feeding the LLM a lot of context. You've got the user's query plus all that external stuff it retrieved.
Right. That can be a huge amount of text.
Huge. And processing that long input, well, it needs serious compute power and memory. So you hit this unavoidable tension.
The trade-off.
The trade-off. Yeah. High-quality responses. That means you probably need more external info, maybe more complex processing steps.
Which means more waiting time, higher latency.
Dramatically higher, yeah. So quality goes up, speed goes down.
So in the past, systems developers, they've kind of had to pick their poison, right? Maximize quality and just accept the cost and delay.
Or the opposite. Focus only on speed, maybe use a fixed, simpler setup, and potentially sacrifice quality.
Because treating quality and speed as separate optimization goals is just easier?
It was the standard approach, but it's not ideal. How do you actually balance those two things, quality and speed, together without making the system impossibly complicated to manage?
And that's where METIS comes in.
That's exactly the challenge METIS was built for. It's really the first RAG system designed to tackle this as a joint optimization puzzle.
Joint optimization, so not just tweaking performance settings after the fact.
No, it's designed from the ground up to jointly schedule the queries coming in and adapt the key Argo settings for each specific query on the fly.
Okay, so our mission for this deep dive then is to unpack those specific settings, the configuration knobs, as the source calls them, that control this quality versus delay balance.
And then show how METIS uses this pretty clever two-step approach to tune those knobs automatically based on the query and what the system is doing right at that moment.
Sounds good. And I think you mentioned there's a pretty compelling payoff here.
Oh, yeah. The headline result, straight from the research, METIS is a serious win for infrastructure efficiency. Compared to the best quality-focused RAG systems out there now, METIS cuts down the generation latency, the waiting time, by 1.64 to 2.54 times.
Wow. It's significant, like double the speed or more sometimes.
Exactly. And crucially, without sacrificing the quality of the answer, that kind of efficiency boost, well, it's huge for anyone running these systems in production.
Okay, definitely worth diving into. Let's start maybe with a quick refresher on our architecture itself, because you said the problem really hinges on where the slowdown happens.
Perfect place to start. So RAG basically has two main stages. Stage one, retrieval.
Finding the relevant info.
Right. The system shoots a query into a database, like a vector database usually, finds the most relevant chunks of text, and pulls them out.
And this part is fast.
Super fast. Computationally, it's pretty lightweight. The paper mentions it's often over 100 times faster than the next step.
Okay, so retrieval isn't the problem, which means step two, synthesis. That's the bottleneck.
That's where the delay lives, absolutely.
Yeah.
Synthesis is where the system takes those chunks it found, combines them with the original user query, and then feeds that whole package into the large language model.
And the LLM has to figure out how to use all that context to generate the final answer.
Exactly. How it processes and combines those chunks, that's the synthesis method. And that processing, that's what dominates the response time.
And here's where it gets tricky for the system, right? Because unlike, say, a database getting a specific SQL query, a Chime-X system just gets natural language. It's underspecified, as the source puts it. The user just asks a question.
Precisely. The system doesn't get explicit instructions on how to execute. It has to guess or figure out the best configuration, how many chunks, which synthesis method for every single query.
Which leads to, I guess, the first big finding in the source material.
It's a huge point. That optimal configuration has to be adapted query by query. You just can't get away with a one-size-fits-all approach.
The data backs this up strongly.
Unequivocally. They found empirically that picking the best RAG configuration for each individual query gets you 12 to 15% better quality.
Right.
And it's 2.5 to 3 times faster, lower delay than using any single fixed configuration for all queries.
Wow. Okay, so that proves it. Dynamic adaptation is essential. Not all questions are the same.
Not even close.
So if we need to adapt dynamically, What exactly is METIS adapting? What are these configuration knobs? You mentioned 3.
That's right, 3 key knobs. And they control both the amount of information and how that information gets processed.
And combined, they create a lot of options.
A massive number of options.
Exactly.
A combinatorial explosion, really. Just as an example, they point out that for just one of the synthesis methods, MapReduce, if you consider, say, 30 different possibilities for how many chunks to retrieve and maybe 50 different lengths for summaries it might create, you're already looking at 1,500 potential configurations.
1,500 ways to answer one query. That's way too many to test in real time.
Impossible. You'd spend more time choosing than answering.
Okay, let's break down these knobs. Knob number 1 sounds pretty straightforward. How many chunks to retrieve? The num chunks parameter.
Yeah, this one seems simple, but it's a classic trade-off. More chunks usually means more potential information for the LLM.
But more processing time, higher delay.
Higher delay, exactly. Because the LLM has to read and process a longer sequence. But there's a catch on the quality side, too.
Oh, it's not just about having enough info.
Nope. If you retrieve too few chunks, obviously you might miss key facts. But if you retrieve too many, especially irrelevant ones, you can actually degrade the quality.
How does that happen?
It's something called the lost in the middle problem. LLMs sometimes struggle to find the important bits when they're buried in a huge, noisy context window. Too much irrelevant stuff dilutes the good stuff.
Okay, so just grabbing everything isn't the answer either. Can you give an example of how different queries need different numbers of chunks?
Sure. Think of a simple factual query like, in what county was William W. Blair born? The answer's probably in one specific document, maybe 2 chunks max.
Right, localized information.
Exactly. But now take a complex one, like when and why did the Voyager 1 spacecraft leave our solar system? You need dates, reasons, maybe context about its mission.
That sounds like it needs info from multiple places.
Definitely. You'd need to piece together information scattered across several documents. That's a query demanding a higher num chunks value.
Got it. Okay, moving to knob number 2. How to synthesize. The synthesis method. This controls the actual processing, right?
Correct. This determines the mechanism the LLM uses to combine the query and the retrieved chunks. There are 3 main ways discussed.
Let's go through them. What's the simplest?
The simplest is called mapper rank. Here, the LLM looks at each retrieved chunk individually. It generates a potential answer based only on that single chunk.
Okay.
Then it scores the confidence of each of those chunk-specific answers and just picks the one with the highest score.
Ah, so it's computationally cheap. Fewer complex LLM calls.
Much cheaper. Great for those simple single-fact queries like the birthplace one, but its weakness is obvious.
If the answer requires combining facts from, say, chunk A and chunk B...
MapRank will completely fail. It can't do that cross-chunk reasoning.
Okay, so if a MapRank is too simple for complex questions, what's next? Stuff.
Right, the stuff method. This one sounds simple, too. Just concatenate or stuff all the retrieved chunks together with the query into one single massive prompt.
And feed that whole thing to the LLM in one go.
One big call. So in terms of LLM calls, it's efficient just one.
But I sense a but coming. You mentioned memory issues earlier.
Exactly. This method is very memory intensive. You're asking the GPU to hold that potentially enormous combined context all at once. If it's too big or the GPU is busy.
You hit a wall or a queue.
Right. Plus, it really maximizes the risk of that lost in the middle problem because the LLM has this single, potentially giant block of text to sift through.
Okay, so MapRank is simple but limited. Stuff is memory hungry. That brings us to the heavy hitter, MapReduce.
MapReduce. This is the one you generally need for those complex queries where you have to reason across different pieces of information found in multiple chunks.
Like asking if several people are from the same country, if their birthplaces are in different documents.
Perfect example. You can't answer that by looking at one chunk at a time, or even just stuffing them all together might lose the thread. MapReduce handles this differently. It's a multi-step process. First, it applies the LLM to each chunk individually, but asks it to summarize the key information relevant to the query.
Okay, so you get a bunch of short summaries instead of the full chunks.
Exactly. Then, in the second step, it takes all those shorter summaries, combines them with the original query, and feeds that to a final LLM call to synthesize the actual answer.
Ah, so it involves more LLM calls overall. Map step, then reduce step?
Yes, significantly more computation in terms of total LLM processing, but it breaks down the problem, making it better at complex reasoning and less likely to hit memory limits with one giant call. It's often essential for top quality on tricky questions.
And that leads directly into the third knob, which you said is specific to MapReduce. How long is each summary, the intermediate length?
Right. When you're doing that first map step, summarizing each chunk, you have to decide how long should those summaries be.
Another trade-off, I assume.
Of course, shorter summaries mean the final reduce call is faster because the LLM processes less total text.
But you risk losing important details from the original chunks if the summaries are too short.
Precisely. Not enough context might be carried over for that final reasoning step. So, for our simple birthplace query, maybe a 20-word summary per chunk is fine if you used MapReduce.
But for the complex Voyager question,
You might need, say, 100-word summaries to make sure all the nuances about the when and the why get passed along to the final step.
okay, so 3 knobs. Num chunks, synthesis method, intermediate length for one of those methods. They all interact, creating, as you said, potentially thousands of configurations for a single query.
A huge search space.
And trying to find the best one by trial and error is obviously out. So how does METIS actually navigate this? How does it pick the right settings quickly without spending all its time deciding how to answer?
This is where their two-step innovation really comes in. METIS acts like a smart controller sitting on top of the Argry system. Its whole job is to slash that massive search space before making a final resource-aware choice.
2 steps. What's step 1?
Step 1 is all about quality. Configuration space pruning.
Pruning. Cutting down the options. How?
Well, it uses something they call the query profiler. Now, wait.
Yeah, I was about to ask, didn't we just say more LLM calls are slow? If we're trying to save time using another LLM, this profiler just adding overhead?
That's the clever part. This query profiler is an LLM, yes, but it's usually a much smaller, faster one. And critically, look at its input.
What does it get?
It only gets the original user query text itself, maybe a tiny bit of metadata. That's it. It does not see the massive context of retrieved chunks.
Ah, okay. So its input is tiny compared to the main RIG synthesis step. Orders of magnitude shorter.
Exactly. So it can run very quickly. Its job isn't to answer the question, but to estimate the characteristics of the question.
Profiling the query's intent? Kind of. What characteristics does it estimate?
It estimates 4 key things that help choose the right RIG configuration later. First, overall query complexity, basically, is this high or low complexity.
Okay.
Second, joint reasoning requirement, yes or no. Does answering this likely require combining info across different chunks?
Crucial for picking the synthesis method.
Very. Third, pieces of information required, it estimates a number, like this probably needs about 3 key facts, maybe up to 10.
So that informs num chunks.
Right. And finally, if MapReduce might be needed, it estimates the length of the summarization required, gives a word count range, like 30 to 200 words.
Okay, so this quick profile gives us 4 signals about the query. What happens with that profile?
That profile gets fed into a simple, fast, rule-based mapping system.
Rules, like if complexity is high, then.
Exactly like that. This mapping uses the profile to instantly filter that enormous configuration space down to a much smaller, pruned range of options. Critically, these are all predicted to be high-quality options for that specific query.
How much does it prune?
The paper says it typically reduces the number of configurations to consider by 50 to 100 times. Massive reduction.
Can you give an example of a rule?
Sure. If the profiler says joint reasoning required, no, then METIS immediately throws out MapReduce as an option. It only needs to consider MapRank or maybe stuff.
Got it.
Or if the profiler estimates pieces of information required, 3, the rules might restrict the num chunk setting to a narrow range, maybe 3 to 9 chunks, instead of considering all 30 possibilities.
Okay, so step 1 uses a quick profiler and rules to basically solve the quality part of the problem, ensuring we only consider configurations likely to give a good answer.
Precisely. We've dramatically reduced the risk of a low-quality outcome, but we haven't solved the speed or delay problem yet.
Right, because the actual speed depends on what the system is doing right now. Congestion, available resources.
Exactly. Which brings us to step 2. Joint configuration scheduling adaptation.
Joint adaptation, making the configuration choice and the scheduling choice together.
Yes, this is the other key insight. After step 1 gives us that small set of high-quality configurations, the system can't just pick the one that looks fastest on paper, like in a vacuum.
Why not?
Because the fastest on paper might not be the fastest in reality if it needs resources that aren't currently available. This leads to what the researchers highlight as the GPU memory pitfall.
Okay, walk us through that pitfall. You said earlier this is kind of counterintuitive.
It really is. Let's say after step 1 pruning, METIS has 2 good configuration options left for a query. Config A uses the stuff method.
Okay, the one that makes one big memory request.
Right. And config B uses MapReduce.
The one with multiple steps, but maybe smaller memory needs per step.
Correct. Now, normally you'd think config A stuff should be faster end-to-end, right? It's just one main LLM call versus several for MapReduce.
Yeah, computationally it seems simpler.
Computationally, maybe slightly less total work. But imagine the system is busy. Maybe another big query is already running and using most of the GPU memory.
Okay.
Config A comes along, needs that huge chunk of memory for its stuff operation, but the memory isn't free. What happens?
It has to wait. It gets stuck in a queue.
Exactly. It gets scheduled, but it can't execute immediately. That waiting time adds directly to the user's perceived latency. Could be seconds.
Okay, so config A is waiting. What about config B, the MapReduce one?
Now, config B involves more steps, yes, but each step summarizing chunk 1, summarizing chunk 2, then the final combination might require a smaller amount of GPU memory at any given time.
Ah, so even if the total GPU memory available is low?
One of those smaller MapReduce steps might actually fit into the available memory right now.
So it can start executing immediately, even though it has more steps overall.
Precisely. By avoiding the queue, config B, MapReduce, could finish and return the answer to the user faster in terms of total end-to-end delay, even if its individual LLM steps took slightly longer in total compute time than config A's single step would have.
Wow, okay, that is counterintuitive. The seemingly more complex option can be faster because it fits the available resources better.
That's the core idea of the joint scheduling. Don't just pick the config with the lowest theoretical compute time, pick the best config that can run now.
So how does METIS make that final choice in step 2? It has the prune list of high-quality configs.
It uses what they call a best fit strategy. For every configuration still in the running after step 1, METIS quickly calculates how much GPU memory that configuration would require.
Okay.
Then it looks at the current available GPU memory. It selects the configuration from the high-quality list that actually fits in the available memory.
Right.
And among those that fit, it picks the one with the highest memory requirement.
Wait, why the highest memory requirement? Wouldn't the lowest be safest or fastest?
Not necessarily for quality. Remember, step 1 already guaranteed all these options are high quality. Within that high quality band, the configuration that uses slightly more resources, maybe retrieving 6 chunks instead of 5, or using slightly longer intermediate summaries in MapReduce, often corresponds to marginally better quality.
Ah, I see. So within the set of options they can run immediately without queuing, pick the one that pushes the quality boundary the most. Maximize quality given the current resource constraints.
You got it. It's maximizing quality using the largest resource footprint it can successfully execute right now.
That's a really systematic way to handle that quality delay tension dynamically. Okay, let's wrap this up by looking at the results. Did this actually work? They tested it on 4 different RAG question-answering datasets.
Yes, Squad, Music, KGARC FinSec, and QMSUM, a good mix of complexities. And the performance gains were really impressive.
We mentioned the latency reduction upfront, 1.64 to 2.54 times faster response time compared to other quality-focused methods like adaptive RAG.
Right. Huge win for the user experience.
Yeah.
But it also improves the overall efficiency of the server hardware itself.
How so? Throughput.
Exactly. Compared to simpler baselines that just use one fixed configuration all the time, METIS achieved 1.8 to 4.5 times higher throughput.
Meaning it could handle almost twice to over 4 times as many queries per second on the same hardware.
Yes. Because it's constantly optimizing how resources are used, avoiding those GPU queues and bottlenecks, it keeps the expensive hardware much busier, processing more queries concurrently. Better utilization.
And that has to translate to cost savings, right?
Yeah.
Especially with how expensive GPUs are.
Absolutely. The research makes a strong point about cost efficiency. They calculated the dollar cost. Even when you factor in the tiny cost of running that METIS profiler LLM,
Yeah.
METIS ends up being significantly cheaper, up to 6.8 times lower cost than trying to get similar or often worse quality by just throwing a massive, super powerful model like Llama 3.1, 70B, or GPT-4o at the problem with a fixed configuration.
So smarter optimization beats brute force compute.
Okay.
essentially. You get better or equal quality, faster responses, higher throughput, and it costs less.
That's the trifecta, yeah.
And just to put my earlier concerns, bed that profiler overhead. You're sure it's small.
Completely negligible in practice, the paper quantifies it. The profiler's delay typically adds only about 0.03 to 0.06, like 3 to 6% of the total end-to-end response time.
Tiny.
At absolute most, maybe a tenth of the total time in some edge cases. The time saved in the main synthesis step by picking the right configuration and avoiding queues massively outweighs that tiny profiling cost.
Okay, deep dive complete. That makes a lot of sense. So summing up METIS, its success comes from tackling that quality delay problem head-on, systematically, in two main stages.
Stage 1. Use that lightweight LLM profiler to get a quick read on the query's complexity and needs. Use that profile with simple rules to slash the possible configurations down to just a small set of high-quality candidates.
Solves the quality problem up front. And then stage 2. Look at that high-quality set. Figure out the resource needs, especially GPU memory for each. Check current system availability, and make the final configuration choice jointly with the scheduler.
Picking the best fit, the highest quality option that can run right now without waiting, solves the delay problem dynamically.
And the big takeaway here maybe isn't just METIS itself, but the whole approach.
I think so. This methodology, using a profile of the natural language input to intelligently guide resource-aware system tuning, that seems really powerful and extensible. It's not just for basic RAG.
What do you mean? Where else could this apply?
Well, think about where RAG is heading. We're seeing things like agentic RAG systems.
Where one query might trigger multiple steps, planning, maybe even subqueries.
Exactly. Or multimodal RAG, pulling in not just text, but images, audio, maybe structured data too. These systems are way more complex.
That have even more configuration knobs, more potential trade-offs.
For sure. Imagine needing to decide how many planning steps an agent should take for a complex task, or what specific combination of text and image retrieval is best for a multimodal query.
So you could use a profiler, like in METIS, to estimate those needs from the initial query.
That's the potential. Profiling the user's intent to guide not just chunk retrieval or synthesis method, but maybe the number of agent steps or the types of data to fetch, making that joint resource quality optimization even more critical as these systems get more sophisticated.
So the core idea of METIS smart AI-driven profiling to manage the quality resource tension could be a key building block for next-generation AI systems.
I think it has that potential, definitely. The tension isn't going away, but maybe we have better tools now to manage it intelligently.
A fascinating look at optimizing the engine under the hood. Thanks for joining us for this deep dive.